accurate assessment of cutaneous tissue oxygenation and vascular function is important for appropriate detection, staging, and treatment of many health disorders, including chronic wounds. Here, cutaneous tissue oxygenation and tissue vascular thermal reactivity are imaged non-invasively using a novel dual-mode imaging system that integrates an infrared camera, a CCD camera, a liquid crystal tunable filter, and a high-intensity fiber light source. Oxygenation changes are induced in the arm tissue of a healthy subject using a blood pressure cuff, monitored by the dual-mode imaging system, and compared with simultaneous measurements of deep tissue oxygenation and cutaneous tissue oxygen tension. Tissue temperature changes in response to external thermal stimulation are also recorded to reconstruct the vascular thermal reactivity map. The cutaneous tissue oxygenation map and the tissue vascular thermal reactivity map are fused through an advanced co-registration algorithm.
In this work, we describe the development of a novel imaging system for the non-invasive monitoring of wound tissue oxygen saturation, as well as dynamic thermographic profile, which helps study exothermic inflammation, and in tracing warm blood flowing into the wound tissue during the post-inflammatory angiogenic phase.
From a clinical perspective, this imaging system has the potential to help answer key questions in the field of acute and chronic wound management, such as using image-guided debridement. It will also help monitor responsiveness of the wound to therapeutic interventions non-invasively by way of repeated measurements of tissue oxygenation.
This dual-mode imaging system, developed at The Ohio State University's Comprehensive Wound Center, is the first step toward the simultaneous assessment of wound tissue oxygenation and vascular function. As you will see, the system is now ready for functional test. Efforts are in progress to improve the engineering design, standardize the protocol, and validate the system for routine clinical use.
In addition to the imaging hardware and the reconstruction algorithms, we have developed fast image co-registration methods for integrating and visualizing overlaid images acquired by the different imaging modalities. The approach is modular, leaving room for future addition of new imaging platforms.
Begin by having a healthy subject sit with his or her left forearm resting on a countertop. Use a brush to paint a thin layer of India ink on the subject's forearm to mimic different skin colors. Place 4 fiduciary markers on the subject's forearm to define a region of interest, or ROI, that consists of both the ink-painted skin and the regular skin. The fiduciary markers have simultaneous thermal and optical contrasts that facilitate image co-registration. Here, a dual-mode imaging system developed at the Comprehensive Wound Center of The Ohio State University is used. The imaging system consists of an infrared camera, a CCD camera, a liquid crystal tunable filter, and a high-intensity fiber light source. To perform multispectral imaging of tissue oxygenation, turn off all external light sources. Then have the subject position his or her arm and capture images. The imaging software automatically calibrates the exposure times at each wavelength. After the sample images are collected from the region of interest, place a whiteboard in the imaging area and acquire reflectance images at different wavelengths. These will be used for calibration. Once the reference images have been acquired, calculate the reflectance ratio and derive the tissue oxygenation at each pixel based on the wide-gap second derivative spectrum. For comparison, acquire a cutaneous tissue oxygenation map using a commercial system. To determine whether change of skin color affects oxygenation measurements in each system, use statistical analysis software to perform a student's t-test comparing the measurements in the regions with and without ink. Next, place a pressure cuff on the subject's left upper arm. Determine and record the subject's systolic and diastolic blood pressures. Place the sensors of an Oxyplex TS tissue spectrophotometer and a TCM transcutaneous oxygen monitor on the same arm and turn on the devices to warm them up for 20 minutes. While monitoring the cutaneous tissue oxygenation map, introduce oxygenation changes in the arm tissue by performing a post-occlusive reactive hyperemia, or PORH. Click the Start button to begin imaging. Monitor the pre-occlusive baseline for 2 minutes. Next, inflate the blood pressure cuff to 50 mm mercury above the systolic pressure to induce a suprasystolic occlusion. Leave the cuff inflated for 2 minutes, continuing to monitor changes in tissue parameters. Finally, rapidly deflate the pressure cuff to induce reactive hyperemia. Record all the tissue oxygen parameters for 2 minutes. To perform dynamic thermographic imaging, have a healthy subject comfortably sit with his or her left arm resting on a countertop. Position the dorsum of the left hand up toward the infrared camera unit of the imaging system. Next, place a laser Doppler probe on the fingertip of the left hand to continuously monitor skin perfusion at a sampling rate of 10 Hz. Place a pressure cuff on the subject's left upper arm. Then determine and record the subject's systolic and diastolic blood pressures. Generate different levels of vascular occlusion by controlling the inflation of the pressure cuff at the following pressure levels: no occlusion, 0.5 times the diastolic blood pressure, 0.5 times the diastolic blood pressure and systolic blood pressure combined, and 1.5 times the systolic blood pressure. Next, perform thermographic imaging tests at 2 vascular occlusion levels, no occlusion and suprasystolic occlusion. At each vascular occlusion level, introduce a thermal stimulation by placing a room temperature water bag on the left hand for 30 seconds. Immediately after the removal of the water bag, start acquiring thermographic images continuously at an imaging rate of 2 frames per second. Using software, determine the tissue vascular thermal reactivity function. Calculate the function index at each pixel of the thermographic image by taking the ratio between the square root of the thermal stimulation duration and the corresponding tissue temperature change. Calculate the finger vascular thermal reactivity value at each occlusion pressure by averaging 5 ROIs in the tissue vascular thermal reactivity map. The finger vascular thermal reactivity values are compared with laser Doppler measurements of finger vascular perfusion at different occlusion levels. To co-register the oxygenation map obtained from multispectral imaging and the vascular function map obtained from dynamic thermographic imaging, use MATLAB to transform all the images to grayscale. Then normalize the pixel intensity values by setting them between 0 and 1. Next, on the oxygenation map or multispectral image, identify the foreground, or skin region with pixel intensity values greater than the empirical global threshold of 0.8 times the mean intensity value of the whole image. Further improve the image using the morphological operation. Next, to accommodate the illumination variation, identify the fiduciary markers. These markers will appear as darker regions in the foreground and will have intensity values below the global and adaptive local thresholds. Refine the fiduciary marker regions using morphological operations to remove noise in the image. Select the centroids of these 4 regions as control points in the optical photo. Repeat similar steps to identify marker regions in the vascular function map or the thermographic image. Match the 2 sets of control points based on proximity. After normalizing them to the same scale, match a control point in the first image to the closest control point in the second one. Compute an affine transformation with translation, rotation, and scaling information between the 2 images using the vascular function map as a reference. Then transform the oxygenation map using the computed transformation. Finally, overlay the co-registered images for visualization. A reconstructed cutaneous tissue oxygenation map acquired from the forearm of a healthy subject using the Comprehensive Wound Center dual-mode imaging system is shown here. Note that significant oxygenation differences between the painted and non-painted tissue regions are not observed. 10 ROIs were randomly selected from outside and within the ink-painted region to evaluate oxygenation measurements. The results shown here suggest that tissue oxygenation measurement by the Comprehensive Wound Center system is not significantly affected by skin color. In comparison, tissue oxygenation measurements acquired using a commercial system are significantly affected by skin color. The Comprehensive Wound Center imaging system is able to monitor changes in cutaneous tissue oxygenation continuously throughout baseline, occlusion, and hyperemia phases of the PORH procedure. During the PORH procedure, the change of cutaneous tissue oxygenation coincides with changes in deep tissue oxygenation. The comprehensive wound center imaging system is also able to image the cutaneous tissue vascular thermal reactivity. These figures show representative vascular function maps of the same subject at different vascular occlusion pressures introduced by a pressure cuff. The averaged vascular function index at the fingertips of the subject correlates with the laser Doppler measurement of fingertip skin tissue perfusion. The oxygenation map and the vascular function map acquired by the imaging system are fused by a co-registration algorithm. This figure shows a representative image fusion.
What we have here is a dual-mode imaging system for simultaneous assessment of cutaneous tissue oxygenation and tissue vascular thermal reactivity. Other platforms, such as fluorescence imaging, can be added.
System integration of hardware and software components represents a key cornerstone in this effort. The image co-registration algorithm in this system can be easily adapted to accommodate additional imaging modalities, making this a versatile product.
After watching this video, you should have a good understanding of the promise offered by this new imaging approach. Development of the system is an example of interdisciplinary translational research at The Ohio State University's Comprehensive Wound Center. Good luck with your experiments.